I'm going to be talking about how one can build a startup out of their studies here at the university. I'm going to go through a bit of a timeline, what resources are available in Canada for this kind of stuff. But I did my undergraduate degree at the University of Toronto in applied mathematics. And I didn't initially want to do a startup. Neither did I initially want to do quantum at all. I wanted to do finance, investment banking, and to go out and make some money. But then I didn't want to do finance anymore, and I found myself in the math program, and a startup seemed to make sense. It's a lot of work, but you can reap the benefits. You start out with almost nothing. Somebody gives you money, you work really hard, and you end up with a company, ideally, that you can sell for millions of dollars. That's the philosophy of it. But then quantum was very interesting, and so I found myself here at the University of Waterloo, which has this incredible quantum program. I was an undergraduate research assistant initially under Professor Thomas Jennewein, and then I got to do a master's degree. Norbert Lutkenhaus, Professor Norbert Lutkenhaus, was my co-supervisor along with Professor Jennewein, and both of them have a focus in quantum key distribution, cryptography, which is not what the startup is about. It's different. However, one of the points of research that Thomas had was asking the question, what if we take the way we encode light for communications and use it instead for sensing? So if we encode light, we send it out into the environment, it comes back, and we can get more information out of it just by way of having encoded it in the first place. And so having worked on this project, it seemed commercializable, and it's kind of what we ran with. So at the very outset, we worked on patenting this technology, Transformative Quantum Technologies, TQT, which is at the kind of beginning of this journey, paid for partial patenting, which is very, very helpful, especially for a person who has never thought about what it takes to patent something. And for reference, a full patent will run you about $30,000. But to get a provisional done, if you write most of it yourself, $5,000, $10,000 could be enough to get you started. And that's what they were able to help us with. Next, we got a grant from the government to do a market assessment. And this is a really important step because you come out of the lab and you've got this really cool new thing, but who needs it and how are they going to use it? That's not clear at all. And that is critical for you to be able to sell something. Like how someone is going to use it and how much they're willing to pay for it and all of that needs to be assessed. So with a bit of a grant from NSERC and Lab to Market, I took a semester off with the encouragement from my supervisors to go to conferences, to cold call a bunch of people and say, how would you use this if it existed? And at the time, where we were landing was, well, we've got essentially a LiDAR, so a 3D imaging device that worked really far. You could see far. And who needed it seemed to be a little bit defense, a lot trains, but nobody needed it enough where it seemed to be a scalable, venture capital backable kind of company. And then, so this is the group that I got to study with. Thomas is in the middle. Then we went through Creative Destruction Labs. This is a competitive mentorship program, which is an interesting concept where people from a variety of fields, variety of experiences, whether it's scientific, whether it's from investment, help you develop your company over the course of 8 months. And if you're progressing in the way that they expect, they let you continue to go through this program. And so with their encouragement, we applied for NATO Diana. And so at the bottom there in 2024, we went through the NATO Diana program. It stands for Defense Innovation Accelerator for the North Atlantic. And this was a very interesting program because it's intended, so NATO went out and they said, we want to have something similar to DARPA in the US, where we want to develop really new technologies, but specifically for defense. And the way they did this is they said, we're not going to have a big bureaucratic organization. We're going to have a small, agile bureaucracy, but get the tech from industry. So they're looking for startups who can come and solve challenges that they define. And the challenge that they defined for us at the time was quantum sensors, but in the water. And so this included gravimeters, magnetometers, imagers like ours. And what the program consisted of was 6 months, if you got into it in the first place, of developing your business. What does it mean to talk to governments? What does it mean to talk to defense primes? How do you put together financial projections? How do you pitch for defense specifically when you're talking to investors and all that kind of stuff? How do you build a team? What HR problems do you expect to deal with? What security problems do you expect to deal with, specifically when you're talking about defense? And then if you got into the second phases of the program, you got another 6 months of just they give you money, they're hands off, and you go and build the thing that they want you to build. And so we ended up doing some testing in the Halifax Harbor. We realized that our tech does work in the water, which was unexpected because we had been working in the air until that point. And here is what is the real business plan that we came up with. So to get everyone on the same page, we're talking about LiDAR. And the way LiDAR works is it's a sensor that sends out a pulse of light. The pulse of light travels to an object, it bounces off of it and comes back. And the device calculates how long it took the light to travel, and so it can tell how far away that thing was. Usually, LiDAR operates in a scanning fashion, so it will get the whole 3D image of the scene in front of it. But it has a problem. LiDAR's big limitation is the distance that it can achieve, specifically because light gets really faint as it travels through the air. And if your object is far enough, and your light pulse gets faint enough, then by the time it bounces off of something and comes back, there may not be enough light intensity, or in other words, light particles, in the pulse for the detector to tell that there's anything there. And so what we did at Phantom Photonics, we improved the camera side of the LiDAR and the laser side of the LiDAR, let's say. The camera is sensitive to the single particle of light. The laser is equipped with optics that encode the light. Basically, we stamp each particle of light with our signature. So what happens is we send out a pulse of light, it travels really, really far, almost all of the light gets lost, and whatever does come back, we can recognize the few particles, because A, we're operating at the single photon, single particle of light level, and B, those particles are encoded with our signature. So this makes for a very sensitive LiDAR, and we were exploring how this works underwater. And underwater, there are a lot of use cases from the defense perspective, and I'm going to have this defense flavor to this presentation because that's what we were working on through NATO Diana. Sonar has been traditionally the Swiss Army knife of underwater sensing. It is used for communications as well. It is used for 3D imaging. It is used for navigation. It has some problems. First and foremost, it is loud. That's bad from a civilian perspective because we're beaching the whales with the sonar, but also because from a kind of covert perspective, you are not covert if you're using active sonar. You're sending out sound and people can hear you. And then there's also the other problem that sonar does not resolve as finely as one would like. Most of the time when sonar is used for imaging, you have a 3D point cloud that you get out of the image, but the points are 30 centimeters apart. So you can't resolve anything that's fine-grained. And so there are these two kind of aspects that we want to improve on with sonar underwater, and LiDAR improves on both of them. It's quiet, because it uses light, not sound. And it has really fine resolution because it's not limited by the physics of sound. It's limited by the physics of light. LiDAR does exist today underwater. It's really hard to deploy. It kind of sucks because it has to be within about 7 meters of anything that it's imaging to get a reasonable image. Water absorbs light like really, really well, so it doesn't reach where it needs to go. So we get these giant robots. We hook the LiDAR on in front of it where the gentleman is standing, and these robots are kind of very stable. So the waves and the currents and the water won't thrash it around, and that's necessary because if you're coming to within 7 meters of, I don't know, an oil rig, you don't want to crash into it because there are waves and currents. So you need one of these things to keep it stable. Deploying one of these things is kind of a big deal. The robot that was on the previous slide is at the end of this ship. And this big ship needs to be mobilized. There's a mobilization fee. There is a daily rental fee. You have to have a crew of about 50 people on board and off board. And at the end of the day, for 2 days of imaging, you're paying $1 million to get your 3D imaging of whatever infrastructure you want to look at underwater. This is very expensive. Most companies cannot afford it, and the ones that can only do this when it's absolutely necessary, required by government regulation. And so what we came up with is, well, our LiDAR can see farther. It can see 200 meters compared to 7 meters. So we can image from the surface. 90% of everything we want to see in the water is within 200 meters of the surface. No big ship, no 50-person crew, no $1 million expenditure. You can put the LiDAR on a buoy. That buoy can collect data, send it up to a satellite, and back down to the ground. So you don't even need to interfere with the sensors as they exist in the water. They can exist for long periods of time. If previously we could only do imaging for 2 days and get a little bit of information, well, now you can leave the thing in there for a long time. And you can get what they call change detection information. You can either watch a critical juncture in a pipeline to see if someone tampered with it, or you can observe the rate of decay of your steel infrastructure to see how often you need to maintain it. This is an unprecedented capability from a civilian and defense perspective. This is an example, an artistic rendering of the kind of resolution we expect to be able to get as compared to the best that is available today. And so this takes us to where kind of we're going today. We got some interns through the MyTax program. We got a little bit of investment from a Canadian investment firm called QuantaSet. They deal specifically with quantum technologies. They are what is called a technical venture capital firm. Their people are technically trained. They will look at your technology and understand how it works. They'll open the box. They'll sit down with you. They'll write a thesis about your tech to be able to bring other investors in who will give you even more money. Most investors don't have the technical know-how to evaluate whether your tech is even real in the first place, not to mention useful, because as a startup, yes, sir.
Yeah, I was going to ask you, how do other ventures deal with, how do you deal with other ventures who didn't understand the technicality of it? Did they just like not trust you, or what was it like?
You mean the VCs, the venture capital firms? Yeah, so we sit at this intersection between defense, which historically has been a very unfavorable investment for investors. Then there's we do hardware as opposed to software. That's unfavorable. And then we also have quantum, which is exceptionally difficult to understand. And so in general, it's hard to find investors, but the ones that we deal with typically are very specific to one of those 3 Venn diagram circles. And there's a type of VC investment called deep tech, which often includes quantum. It has AI, it has certain biotech, nanotech, anything that requires a lot of knowledge to build and a lot of capital to build. We typically only talk to those VCs. I'll give you an example of why. I sat down with a VC who's a generalist recently, last year, and I gave them the simplest explanation that I could of what we do. Something similar to the explanation that I just gave. In a LiDAR, you send out light, you wait for it to come back, and all that kind of stuff. And they were like, it went way over their head. They didn't even know what to ask me. And the feedback that I got afterwards was the way you should have explained it as, you know how Elon Musk has LiDAR for his rockets? Well, we do that and then just move on. Don't explain anything, right? So there comes a certain point where you have to pick and choose who you're pitching to. The novelty and the significance of what we came up with here can go over certain people's heads. It is a challenge to get that information through to the people you have to get it through, but even when you have someone knowledgeable sitting in front of you, you have to convince them. And there is a process called due diligence that you go through in an investment round where you put together the entire argument from start to finish, whether it's the technical due diligence or financial due diligence, where you have to explain the business model, how you're going to make money, show them the financial projections. It's something that takes a couple of months, usually at least. Last year, we spent 6 months going through financial due diligence with one particular investor. It costs a lot of money. It takes a lot of energy. A lot of thought goes into the specific thing that you just mentioned. Yeah. Yes.
You mentioned a problem with stability when it comes to these LiDAR sensors underwater. So how does the model that you just proposed go against that problem?
Very good. So usually LiDARs have one pixel in them, and it sends out a pulse of light. The light comes back, and it knows that the light came back, and that's enough. We have an array of pixels. So we get an entire image coming back all at once. And light travels very fast. So even if your ship is moving around, we get lots of images, and we stitch them together using an algorithm that's akin to the panoramic functionality in your phone. Yeah.
Sorry, do you mind passing that down? So you mentioned your LiDAR uses, like, I guess, single photons to construct the image. I do a bit of astrophotography, so I know a big problem we have is like dealing with noise. So if you're using like single photons, how do you guys deal with, I guess, all the noise from like surroundings and other sources that, I don't know, might interfere with your sensor's emission of that photon?
It's an excellent question. You hit the nail on the head with what is particular about the tech that we developed. The way we receive the light is, if I were just to put it simply, we have two cameras, not one. And the way we manipulate the light is that one camera receives signal plus noise. The other camera receives negative signal plus noise. So if you can think of the signal as like a sinusoidal wave, one gets plus sign, the other one gets negative sign. And then we take the difference of those cameras. So it's signal plus noise minus negative signal minus noise. The noise cancels out, the signal amplifies. And you have a more sensitive tech. Yeah.
I was just hearing that you encode the light and the light photons. I was curious how you actually encoding your signature onto it. So how does that happen?
We use interferometers. More specifically, we use an unbalanced interferometer. So every photon that goes through this interferometer, and for anyone who doesn't know what that device is, it's one beam splitter and two mirrors. So any photon of light that goes through it will either, just checking, are we good on time? Okay. Will either bounce off of one mirror and leave, or it'll bounce off of the other mirror and go through it. But because of the way quantum works, each photon that goes through actually takes both routes at the same time, and it exits. If the mirrors are at different distances from the beam splitter, that photon will come out at two different places in time at once. And so each particle of light comes out in a superposition of time. We call those time bins. And what is encoded, the function that gets encoded, is the distance between those time bins. So we vary that distance. And without getting into the details of the decoding in the receiver side, what the camera sees is brighter and dimmer light, depending on how far apart those time bins are. So one of the mirrors at the outside is moving back and forth according to whatever function we want. And so the two time bins are getting farther and closer apart for all the different photons that we send. And on the receiving end, the camera will see brighter and dimmer light that corresponds to the movement of the mirror. And so we do a cross correlation in the back end of the light, brighter and dimmer light. And it's getting very complicated, but it's a cross correlation. Yes.
Very cool, yeah.
Yes. Yes.
Sorry.
Yes, absolutely. So that would feed into the noise aspect of it all. Because we have a single photon sensitive detector, what we end up seeing is thermal photon detections. So just from temperature, we get the detector creating its own clicks. So sometimes a photon will get lodged in the detector layer, and then it'll randomly get released, and the detector has a click in it. And so it tells us there was a detection when there wasn't really. So detectors are imperfect. Sometimes they create detections that aren't there. Sometimes they don't count detections that are there, and that's called inefficiency. Most detectors have some baseline of inefficiency. So those are all things that we have to account for. But yeah, does that somewhat answer your question? Yeah. Okay.
So is that why you let the sensor set for long periods of time to reduce that error? Or the detector set for long periods of time, would that reduce the error that you were talking about with stray photons?
Can you say the question from the start for me, please?
So to reduce that error that you were just talking about with stray photons, is that mitigated by letting the detector sit for longer periods of time over like whatever you're trying to scan?
It would be, yeah. So
Okay.
there's definitely a trade-off in use cases. Some people need higher resolution and more certainty in what they're seeing. Some people just need you to scan everything faster. The longer you can sit in the same place and accumulate more light, the more information you have to work with to get rid of the noise and accumulate, certainty about where the thing you're looking at was. So it depends on who we're talking to, how long we actually let the detector sit. Sometimes it'll be half a second, sometimes it'll be 30 seconds. It just depends. There's also somebody up in the far row.
Oh no.
You said previously that the original issue was they had to be between 7 meters to make a good image. How did you resolve that issue with your own technology?
Great. Okay, so we've got a more sensitive LiDAR. What that means, and we say that the biggest benefit is that it can see farther. We don't make the light travel farther necessarily, but because we can afford to lose more light along the way, we end up being able to see things that are farther away. And so we don't have to be 7 meters close anymore. We can be within 50, 100, 150 meters. In the best case scenario, with the most marginal components in our device, we can potentially see up to 200 meters underwater. And so the way we resolve the 7 meters is with the sensitivity of the sensor that we've created and deploying it in environments where it didn't exist before. If anyone has another question, I need you to really wave your arm around at this point. Yeah, great.
So if you're measuring a thing over a period of time and it keeps changing, does the image come out differently?
If the thing keeps changing. Okay, so for example, if you're underwater and you're looking at something and you end up kicking up mud, you're going to have a clear image and then a very noisy image like this. So in that case, if you kick up mud, you have to leave for a couple of hours for the mud to settle. Underwater, it's like that. But you will have to do some human intervention in that signal processing, just looking at the images and deciding which one you accept as information. If it's really changing very fast and a lot underwater, that doesn't happen too much. Nothing moves very fast underwater. Yeah, I think you would just have to redo the image if your images are incongruent, like one after the other over a short period of time. Might be an issue with the electronics, might be something else. It's an unusual situation underwater. If you're in the air, there are scenarios where you might be looking for something that's moving really fast, in which case, if you did have no change in the image and then a quick change in the image, well, maybe you had a supersonic missile go by or something like that. So.
Yeah. I guess a follow-up to that is how exactly you process the images that you get back. It's all done by a computer, right? I'm guessing probably not by a human.
Right. So ultimately, we want to be able to use our tech to detect changes in images underwater. So if you're looking at infrastructure, you want to see if there's a crack in a pipeline. If you're, let's leave it there for now. We have a LiDAR that goes and images a bunch of pipeline, kilometers, hundreds of kilometers of pipeline. You're probably not going to have a human sitting there going through every, image. To that end, we are employing AI in our tech stack. an AI has to be trained. So we have to gather a whack load of data underwater first, which is going to take a while, and that's going to be a big part of our tech roadmap. And then we train the AI, and then it can do that. But in the interim, until then, somebody has to sit there and look at the images. So for the short term, yes, but only to develop the tech to its full potential where it can independently make those decisions. You had another question? I'll let it know.
Is this better than a traditional LiDAR in every use case?
Yes. It works underwater, in the air, and in outer space. In the air, our imaging can go up to 50 kilometers. The state-of-the-art currently, which is owned by the Israeli army and is connected to helicopters to do search and rescue operations, can see up to 5. We have one question down here and one over here.
Okay. So for the software side, do you find yourself having to make most of the software from the ground up, or do you think resources already exist and that you're just applying it for your use case?
For LiDAR imaging, there are certainly resources that exist, and you can buy it's a solved problem in some sense. However, there are risks when you buy other people's software, from having it serviced to having it customized. So there are some things that we do where, yes, we'll buy a software, but a lot of it we do from the ground up. Certainly, if you're trying to make your device portable, you want everything to be on an FPGA and not on a connected desktop. So we have to do that. You have to create graphical user interfaces. We have to hire someone professional to do that. Everything has to be architected. You've got all the softwares that connect to the electronics kind of in the signal processing computer, and then between that and there's a lot. There's a lot of software that goes into this, unfortunately. There's a question here, and then there's one up there.
I was just wondering, because I'm very interested in startups myself, I run a few myself, and like there's an oversaturation in the market because of the AI. All the YC startups right now are all like very similar to each other. So I was just wondering, in the quantum field, is there like, do you feel like the market's saturated, or is it just beginning to develop in like the information field? Because like I really want to get into this in like university. Yeah.
Yeah, I would say that the quantum sector is the opposite of oversaturated. There is a dearth of companies. So we definitely need more solutions. It's very difficult to build a quantum startup because of, you need so much knowledge. AI startups, if you know how to use ChatGPT, you could probably figure out how to connect it to an app. In quantum, you have to have started somewhere where you have very knowledgeable people to either train you, and then you get to that point. And usually there's a professor involved in a quantum startup, which in other instances, for example, if you're in space and you've got a professor on your team, that might not be a good thing because investors will expect that you're going to build an academic science project and not a product company. Whereas in quantum, it's inevitable. You need so much knowledge to build these things that, yeah, you're going to have those people involved. And
Like this mentorship is really important in quantum startups. We get a lot of mentorship.
yes, and I would say also in quantum we need a lot of mentorship because the people who do the science are not necessarily the ones with the entrepreneurship intuition. And there's know-how in building a company. So yes, there is a lot of mentorship involved.
Are those opportunities like possible to like get in undergrad, or like do they start after graduate?
That's a good question. I didn't start in undergrad, so I don't know. I started in graduate school, so I can only speak from my own experience. It is definitely there if you're a graduate student. I'm not sure if it's there as an undergrad.
Thank you so much.
There's another question up there. You're running up and down, John, getting those steps in.
You mentioned it can be used in space, so could you theoretically attach it to a satellite and map planets that we can't go to?
I don't know if you would be doing the mapping from a satellite. So we've had a discussion with Honeywell about mapping the moon at some point, but that would not happen from a satellite, I don't think. I think that would be from a rover. On satellites, however, you could do what they call neighborhood watch, where right now there's an issue of satellites being contacted by other satellites, but like physically. So another satellite will come, orient itself, stay in the shadows, which matters because satellites have regular photo cameras. They can look and see what's around them. But to see it, they need the sunlight. So if something is hanging out in the part of the satellite that doesn't have sunlight, their cameras won't see it. And that's how rogue satellites collect information. We don't have any way of illuminating rogue satellites today because traditionally that takes a lot of power. And satellites are very power scarce. It's just that's how they are. Am I running out of time? Yes, I am running out of time. Yeah, okay. So I'm going to wrap up there. But yes, there are ways of using it in that space. So thank you very much, everyone. I think I have an email on a slide somewhere here. Feel free to contact me. I'm also on LinkedIn. I'd be happy to answer any more questions or take a call with you. Have a great day, everyone.